Okay, so today's lesson is on stoichiometry. And stoichiometry is actually what we build up to. The first 10 or 11 chapters that we do all build up towards stoichiometry. All right, now stoichiometry is nothing more than the math, quote unquote, behind chemistry. All right, and it's used. Are you serious? 72691. Come on, Mrs. Richardson.
You should
Unfreaking believable.
Please save all pages till we let you know.
As I was saying before I was so rudely interrupted, it is used for predicting quantities in a chemical reaction. So we've all seen before a recipe for brownies or cookies or whatever it is, and it always tells us that it makes about X number of servings, or 24 cookies, or 2 dozen brownies, or whatever it is. And that's basically what stoichiometry does. We can take amounts of certain reactants, and we will be able to predict the amount of product that should be formed. And the way we do this is by using a balanced chemical equation, which we already know how to do. We just tested over, so we shouldn't have any problems doing that at this point in time. All right, so in the balanced chemical equation, the reactants combine in specific ratios to form products that are also in exact ratios. So if I have two products, they will combine in a specific ratio, 2 to 1 or 3 to 2 or 4 to 1 or whatever it is, and they'll form products that are also in exact ratios, like 2 to 3 or 3 to 2 or 1 to 2 or so on and so forth. Okay, so let's take a look at a chemical equation, do a little quick review. All right, because a balanced equation actually can be interpreted in terms of different quantities. So Mr. Herzog is going to put up a balanced chemical equation here. And this is one that we use a lot in chemistry because it's a very simple one and provides us an easy way to teach about ratios. So we're going to look at the combination reaction that forms ammonia gas. So we have nitrogen gas plus hydrogen gas, and that will yield ammonia. Okay, so Mr. Herzog is now going to balance this according to the rules we learned back in chapter 11. So the ratio here is 1 to 3 to 2. Okay, now let's look at those ratios a little bit more in depth. First of all, these ratios or these quantities can be interpreted as the number of atoms. So if we were to look at this reaction in terms of atoms, we would be able to determine how many atoms of each element are present. So for nitrogen, N2, there are 2 atoms of nitrogen present. All right, for hydrogen, there's 3 hydrogen molecules, and each molecule contains 2 atoms, so that's a total of 6 hydrogen atoms. All we do is 3 times 2. Okay, so 2 atoms of nitrogen and 6 atoms of hydrogen combine together to yield, once again, 2 atoms of nitrogen, in addition to the 6 atoms of hydrogen. So that NH3, that ammonia molecule, contains 1 atom of nitrogen and 3 atoms of hydrogen. All right, so if we have 2 molecules of that, that's 2 atoms of nitrogen and 6 atoms of hydrogen. So as you can see, the number of atoms in this reaction is conserved throughout the entire reaction. Okay, so we talked about the law of conservation of mass or matter. All right. Okay, where we said matter can either be created or destroyed. So 8 atoms in the beginning. Right, can't be created or destroyed.
At least it
Can't.
can't.
Yeah, nobody cares, Rivich. We have typos in here all the time. All right, it makes the kids laugh at how stupid.
I don't see a typo.
Oh God. Okay. Yeah, so there's an of there. Should have done it black. Anyway, Mrs. Rivich is taking notes, just like you guys, because she has a test to study for. She's frantically taking notes. She doesn't have the option to pause like you guys do and rewind. But you can go on our YouTube. Oh, sorry. So the second quantity that we can talk about is the number of molecules. So remember, molecule is a combination of two or more atoms that are chemically combined. All right, so there is one molecule of nitrogen gas. Okay, so there's one molecule of N2. There are 3 molecules of hydrogen gas, so 3 molecules of H2. And those combine together to yield 2 molecules of ammonia, which is NH3. Okay? Now, we will use these two sparingly in the coming weeks, but the ones that we really want to focus on is the number of moles. If you remember the definition of moles, okay, it's basically a quantity. So like we said, 12 dozen was 12, or 1 dozen was 12 eggs. Okay, well remember that 1 mole is 6.02 times 10 to the 23rd representative particles, or the molar mass, or liters, and all that kind of stuff. And we'll get to that a little bit later. Okay, but the coefficients, all right, the big numbers out in front, all right, so 1, 3, and 2, those coefficients tell us how many moles of each substance are present. Okay, so once again, there's 1 mole of nitrogen gas. Oh, Herzog. Oopsie, oopsie. 1 mole of nitrogen gas plus 3 moles of hydrogen gas. So when those two combine together in that exact ratio, they will make or produce 2 moles of ammonia gas. Okay? All right. So let's move on here. All right, so mole ratios. Okay, so we're going to take what we just used in learning about moles and those coefficients, and we're going to introduce a concept called mole ratios. All right. Remember that any ratio is nothing more than a conversion factor. All right, and mole ratios come from the coefficients of a balanced chemical equation. All right, so Mr. Herzog is going to write all of the mole ratios for the chemical equation. And all we're going to do is we're going to compare 2 different compounds in this reaction. So we're going to start off with nitrogen and hydrogen. And we want to write the ratio of how many moles of nitrogen to how many moles of hydrogen. So there's
a horrible N.
It's okay. Everybody knows you can't write.
I know.
All right, so the mole ratio between nitrogen and hydrogen is 1 mole of nitrogen for every 3 moles of hydrogen.
Now we're going to compare the nitrogen to the ammonia. So for every 1 mole of nitrogen gas present, we have 2 moles of ammonia. All right, so all we're doing is we're taking each element or each chemical or each compound, and we're comparing it to the other ones present in the formula. Now we're going to practice writing all of the mole ratios, so when we do have to pick the 2 that we actually need, we're able to do that. All right, so we compared nitrogen to the hydrogen, and now we're comparing the nitrogen to the ammonia, which I did right here. Now what we have to do is we're going to compare the hydrogen to the ammonia. So we're going to say for every 3 moles or for every 3 molecules of hydrogen gas, there are going to be 2 moles of ammonia produced. Now, there's going to be 6 mole ratios for this particular example, because once you find your first 3, all you do is take the inverse, that means flip them around like this, and you get the other remaining mole ratio. So we can say for every 3 moles of hydrogen gas present, there is 1 mole of nitrogen gas. For every 2 moles of ammonia, there is 1 mole of nitrogen gas. And then we take the inverse of this one also, and then we say for every 2 moles of ammonia produced, there are 3 moles of hydrogen gas.
Okay, so we'll give you kind of a second to write all those down. Really? I hope that's not on
Bless you.
the recording.
Thank you.
You're welcome.
You know, it'll sound like Perry's really nice in the recording, and like you.
It's alright, they know I'm not
I
nice.
know I'm nice. I like this color. I like this color today. I'm gonna use it next.
Okay. They can pause and write these down. Let's move on.
Let's move on.
Let's move on. All right, so let's do some molar conversions here. So Mr. Herzog is going to write down our 6 mole ratios that we... I'm not forcing it. Write it down.
Okay, all right. So you have 1 mole of N2
You
for
want me to write- Are
every.
you writing in pink?
It's fuchsia.
Okay, whatever.
Moles of H2. We have, let's see, 1 mole of N2 for every.
2 moles of NH3.
I don't have my glasses. I can't see.
It's right there.
Oh yeah, it's right there. 2 moles.
3 moles.
Dyslexia got me again.
Your dyslexia.
Did I have to write all 3? Or all 6?
Yep, you have to write all
Oh,
6.
sweet. Now, for you guys at home, you don't have to do this because you just wrote it down.
You're not at home, you have to write it down. Mouse man, active out God.
All right, okay, and my hand's cramping. I know what the students feel like.
I know, they gotta write all the time.
I don't like it.
Too bad.
I'm sorry, students.
Okay,
I don't like
So-
it anymore.
we're going to do some molar conversions. Okay, so we're going to have some hypothetical situations here where if we have a certain amount of reactant, how much product should be produced in that reaction. So the first one we're going to do is we want to know how many moles of ammonia gas are produced if in the beginning of the reaction we start with 2.25 moles of hydrogen gas.
Okay, so what I'm going to do is I'm just going to go ahead for a second and move to the next page so we have more room to work our work out in. To show the problem. All right, so if we have this right here, if we have nitrogen gas plus hydrogen gas and that arrow NH3, let's balance this. You put a 2 here and a 3 here. These are where we got our mole ratios from. Now, what I like to do is if in our example, when we start a stoichiometry problem, write down what you know for that chemical and write it underneath. So we go back and it says we have 2.25 moles of hydrogen gas. So what I'm going to do is I'm going to put that we have 2.25 moles of hydrogen gas, and I'm going to circle that chemical. Now, let's go back to the problem, and it's asking how many moles of ammonia are produced. So we're looking for how many moles of ammonia we have. So I'm going to circle this. Now, by circling this, you can see that my mole ratio that I'm going to use is between this chemical and this chemical right here. Okay, so let's go back for a second, and I'm going to show my work actually right here. So if we have 2.25 moles of hydrogen gas, this is just nothing, or this is nothing but a dimensional analysis problem where our units are canceling out, and I have to figure out, well, I need hydrogen and I need ammonia. So I'm going to look for which of these 6 conversion factors cancels my hydrogen gas out and has ammonia. So it's actually going to be this one right here. This is the one I'm going to use, and that's what I multiply. Alright, so I put 2 moles of NH3 on top and 3 moles of nitrogen. Oh, it's not an N. 2 moles of hydrogen gas on the bottom. Now, notice my units cancel out, and I'm left with the unit that I want right here, moles of NH3. So I take my number, 2.25, multiply it by 2, divide it by 3, and I get 1.50 moles of NH3. Now notice right here, I include all units in all chemicals. You don't want no naked numbers. You must have a unit. You must have a chemical with your numbers, or else you'll get your problems marked wrong.
Chemical label. I like the word labeled. Naked's bad.
I like no naked numbers.
No naked numbers, that's bad.
Yeah.
Kids remember naked numbers more.
They like, yeah, they.
That's
never
true.
mind. Okay.
Bad kids.
All right, let's do. What's example in Spanish? Ejemplo? I've been saying that, and no one's corrected me yet. Example 2.
I think it is.
That's what I thought. Kids yelled at me and said that's not.
I think
Oh well. How many moles of nitrogen gas are needed to produce 16.2 moles of ammonia?
Okay, so here's an example of a problem where we have a required amount of product, so we need to know how much reactant do I need. So for example, if you were building something and you knew that you needed to make 3 tricycles. You would know that in order to make 3 tricycles, you'd have to have a minimum of 9 wheels. Okay, so that's kind of what we're doing here.
Okay, so let's take a look at this problem. It says if we have 16.2 moles of ammonia, and I'm looking for moles of N2, which are right here. I want to know how many of those are actually needed to produce this much ammonia. It's pretty simple. So we start with our number, 16.2 moles of NH3, and I have to find my mole ratio that cancels this out. Now, I know I want ammonia to cancel, so I'm going to put moles of ammonia down here, and I want moles of nitrogen to cancel. So I know which ones I need. Now I just have to figure out what the numbers are. Well, the the coefficients right here, that's a 1, okay? They simply tell me what the mole ratio is. So I'm going to put a 2 down here and the 1 right there. Now, if I did this correctly, my units will cancel out, and in this case they do, and I'm left with moles of nitrogen gas. So I take 16.2, divide it by 2, and the 3 sig figs, 8.10 moles of N2. You probably wish I didn't said the word sig fig, but yes, they do count here. So how many you start with, I started with 1, 2, 3 significant figures. My answer will have 3 significant figures as well. All right, thank you for watching.